So we're going to go ahead and work some additional practice problems for Chapter 8. Again, if you're watching this video, you are clearly on YouTube or linked through D2L to watch these. I recommend working these problems on your own first to make sure you're comfortable. Once you know you're comfortable with them, then go ahead and you can start working them, looking at the key, looking at this video. This key is only written out in this video, so you must watch this to get the actual key. But let's go ahead and work through a series of problems for the content from Chapter 8. So number 1, calculate the wavelength of an electron that's traveling at 2.65 times 10 to the 6 meters per second. Here we've got your velocity and we've got wavelength. We can use our de Broglie equation to solve this question. The de Broglie equation is relating that wavelength of a particle to its velocity. So now we know wavelength equals Planck's constant divided by the mass times velocity. So h is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. M is your mass. This is in your SI based units. SI units for mass is actually kilogram. We use gram all the time, but it is kilogram. An electron weighs 9.11 times 10 to the minus 34, or 31, I apologize, 31 kilograms. The only reason I remember this is that for some reason I just think of 911 and then I think of Halloween and it clicks for me. I'm trying to make this a lowercase k. I'm not doing a very good job. You don't have to know the mass of the electron. On an exam or quiz, I would give it to you. Since this is additional work outside of class, you guys can look that up. And your velocity, remember v is velocity, nu is frequency. They look very similar in font. 2.65 times 10 to the 6th meters per second. So now it's just a plug and chug type thing. 6.626 times 10 to the minus 34 joule seconds divided by 9.11 times 10 to the minus 31st kilogram times 2.65 times 10 to the 6th meters per second. If I plug this in my calculator, I'm going to get an answer of 2.74 times 10 to the minus 10th meters, which I can also rewrite as 2.74 angstroms. You guys haven't learned angstroms explicitly, at least not in my class, but angstrom is 10 to the minus 10th, and it's often how bond lengths are measured. But the bigger question is, how the heck did I get to meters from the units I had above? This is where we need to remember that joules is what we call a calculated unit. A joule is a kilogram meter squared per second squared. So I've got that times a second divided by kilogram times meters per second. My kilograms are going to cancel. This second cancels with one of my seconds here. One of my meters here cancels with meters here, and my last second here cancels with seconds here, leaving me meters for my final answer. Joules will throw students off, so you need to be comfortable with that and understand that joules are, in fact, kilogram meter squared second squared, or per second squared. You can also write that as kilogram meters squared second to the minus 2. That the minus sign shows you it's the denominator, but you need to remember that so you can get to the correct units here. What is an emission spectrum, and how does an emission spectrum of a gas in a discharge tube, think of lab, I know you guys haven't done this in lab, so that comment's probably not as helpful to you, differ from a white line spectrum? Some people, most schools do this do a lab like this in lab, and unfortunately you guys don't have a first semester lab here, so you guys didn't get to do it, but a lot of students do this in lab. Anyway, let's go ahead and look at it. What do I mean by this? What's an emission spectrum? Emission spectrum, first of all, emission spectrum is when the electrons are going back down to their ground state. So the energy is being emitted in the form of light. So the light's released, the electron, when that light releases or allows the electron to travel back down to its ground state, it releases that energy in the form of a photon, h nu. So the electron travels from the excited state back down to the ground state, and when it does that, it releases a photon. Again, we use h nu to represent a photon because that's going to represent the energy of the specific photon being released. So line spectrum is what we see from a gas discharge tube. When we see this, what we're going to have here is you're going to have some kind of spectrum, and it will all be black in here. But you're going to have very specific lines. So you have a purple line, maybe a blue line, maybe a red line. It's very discrete lines. A white light spectrum, on the other hand, is just that. It's the entire rainbow. So you'll have your red into your orange, to your yellows, to your greens, blues, indigo, which I never remember what indigo actually looks like, and purple. So white light spectrum is continuous lines. Again, this is why if you actually see somebody wearing a white shirt, they're actually reflecting every color in the rainbow back at you at one moment in time. It's taking the light from the sun or whatever light source it has, and it's reflecting all colors back at you at the exact same moment in time, and your brain is processing that as white. If you see black, it's because it's absorbing all color and all you see is nothing. So, what is the characteristic wavelength associated with a baseball thrown at 95 miles per hour? We're given that the mass of a baseball is 5 ounces, 16 ounces is 0.4536 kilograms, and 1 mile is 1.609 kilometers. Well, to do this, I need the Broglie equation. So lambda is going to equal h over mv. Because I want wavelength. I need to know that. I've got velocity here. So I know that I'm going to be dealing with the Broglie equation. H is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. M is mass, but I need this in kilograms. I currently have this in ounces. And V is velocity, which I need in meters per second to cancel out my joules. And I currently have it in miles per hour. So I will have to do a series of conversions before I can actually use my equation. Let's go ahead and convert our mass first. The mass of the baseball is 5 ounces. 5.0, don't forget that 0.0 is your sig figs. I've got 0.4536 kilograms for every 16 ounces. I've been asked a couple times now by students if I need to keep this 0 here. The answer is yes. One, sometimes students will write such a little point and then they'll write 4536 and they forget that decimal point. They don't see it and it messes up their calculations. Two, it's just proper. So yes, please include that. This equals 0.14 kilogram. 2 sig figs, 2 sig figs. I also need my velocity in meters per second. I've got 95 miles per hour. Now again, you can convert the distance first or the hours first. I'm going to convert the distance first just because it's the numerator. Times 1.609 kilometers per 1 mile times 1,000 meters per 1 kilometer. If I stopped right here, this cancels my miles and my kilometers, and I've got meters, so I'm halfway there. Now I just need to convert my time. I know that there is 1 hour for every 60 minutes and 1 minute for every 60 seconds. Cancels my hours, canceling my minutes. I've now got the units I want. Calculate this out, and I get 42 meters per second. 2 sig figs, 2 sig figs. Now let's go ahead and make some room on the slide. So now we're ready to go ahead and use the Broglie equation. Lambda equals 6.626 times 10 to the minus 34 joule seconds divided by the mass, 0.14 kilograms. Don't forget that zero, that leading zero, it's just a placeholder, times 42 meters per second. Calculate this out, and we get 1.1 times 10 to the minus 34 meters. And we just learned 2 examples ago how we can get all these units down to just meters. So if you're unsure of how we got to meters there, please look at example 1, and you'll see how that does in fact give us meters. And see, that is a perfect example of drawing the decimal place and it not really showing up. 1.1 times 10 to the minus 34 meters is the wavelength of the baseball thrown at 95 miles per hour. It's a pretty long wavelength. 95 miles per hour seems fast to us, but in the terms of wavelength and correlated back to energy, it's really not that fast. Calculate the wavelength of a radio signal with a frequency of 100.7 megahertz. So wavelength, we're looking for wavelength here, and we're given frequency. We know lambda is equal to c over nu. C is our speed of light. 2.998 times 10 to the 8th meters per second. 100.7 megahertz. Megahertz is 10 to the 6th hertz, so I need to convert that. You can do this in a separate equation or in this equation together. I'm going to do it in the same equation. 10 to the 6th hertz for every 1 megahertz. I get out 2.98 meters. Radio signals are pretty long, relatively speaking. If you remember, you should remember the electromagnetic spectrum, and they're pretty, they're on the long, low energy side, so it makes sense that it's a longer wavelength. Which of the visible colors of light has the highest frequency? And what does this mean about its wavelength? Well, this is, remember, I want you to be careful with this. What do we mean by energy, frequency, and wavelength? So the electromagnetic spectrum, we usually write it with our radio waves all the way to our gamma rays. Increasing this way is our wavelength, but increasing this way is our energy and our frequency. So, visible colors of light is our Roy G. Biv. Visible colors meaning what colors do we see. But I warned you guys that the way we memorize this is actually backwards to the electromagnetic spectrum. So this actually goes V, I, B, G, Y, O, R. If we want to correlate it on the wavelength or on the electromagnetic spectrum itself. So which one has the highest frequency? Violet, which we often call purple. What does this mean about its wavelength though? Well, we know that the higher the frequency, Because remember, frequency is cycles per second. Means higher energy, but shorter wavelength. This compared to this. If this is 1 second, if this distance here is 1 second, we're getting more of a wave in here, more of a complete cycle than we are over here, partial cycle. So higher frequency, higher energy. So let's go ahead and look at a couple more examples like we just did in number 4. Calculate the wavelength of each frequency of electromagnetic radiation. I know this may seem repetitive. These equations, though, should be like muscle memory for your brain. You need to be able to quickly see them and be able to calculate it quickly. So if we see calculate wavelength for each frequency, we know we can use the relationship lambda equals c over nu. C being your speed of light. Now, I memorize this as 2.998 times 10 to the 8th meters per second. You are fine memorizing this as 3.00 times 10 to the 8th meters per second. They have different number of sig figs though. So depending on what other values you're given, you need to pay attention to your sig figs here if this limits it. If it does, that's fine. I don't care. This has 3 sig figs, this has 4, but make sure you're using the right number of sig figs in your final answer. So 2.998 times 10 to the 8th meters per second divided by 100.2 hertz. A hertz, 1 hertz, equals 1 second to the minus 1. It's 1 cycle per second. So I'm going to replace this with seconds to the minus 1 just so it's very clear on my units here. When I calculate this out, I get 2.992 times 10 to the 6th meters. 4 sig figs, 4 sig figs, 4 sig figs. Again, if you'd use 3.0 there, you would have 3 sig figs here. And 1070 kilohertz. Lambda is equal to c over nu, 2.998 times 10 to the 8th meters per second. 1070 kilohertz. Kilohertz is 1000 times greater than a hertz. Takes 1000 hertz to reach 1 kilohertz. And when you make sure you're calculating that out correctly, when I calculate this out, I'm going to get 280, but I need to put a decimal place here, meters. So I have 3 sig figs here. This 0 is not significant on the end, but my final answer was 280. If I write it like that, that's only 2 sig figs. I must include that decimal place to specify that that 0 is in fact significant. Calculate the wavelength in nanometers of light emitted when an electron and a hydrogen atom makes each transition. Remember, you can do this either separately or together. I do the equation together. You can calculate each one by itself, meaning that you can calculate negative 2.18 times 10 to the 18, negative 18 joules times 1 over n squared, and then subtract the second one from that and do those in pieces. I do this all in one piece though. I'm going to do this as this equation, n squared final minus 1 over n initial squared. I want wavelength in nanometers of light. If I'm transitioning between two things, I'm only calculating energy. So I'm also going to have to use E equals hc over lambda rearranged to calculate my wavelength. So for the first example, n equals 2 going to n equals 1. This is n initial, this is n final. Negative 2.18 times 10 to the negative 18th joules times 1 over 1 squared minus 1 over 2 squared. Be careful plugging this into your calculator. Use parentheses when appropriate. And you should find the answer to be negative 1.64 times 10 to the negative 18th joules. Why is the answer negative there? Well, I'm going from an n equals 2 to an n equals 1 level. I'm emitting light, so I'm losing energy. So therefore, it's negative sign, and the negative is just representing that the energy is being given lost from the electron, not from it being gained. That's the only reason it's negative. I'm going to take the absolute value of that and make it positive when I do the calculation for wavelength, because wavelength is a distance. It's not going to be a positive or a minus sign on the wavelength. Lambda equals 6.626 times 10 to the minus 34 joule seconds. C is your speed of light, 2.998 times 10 to the 8th meters per second. And the energy we just calculated, 1.64 times 10 to the minus 18 joules. Again, I'm keeping this as a positive here because the negative or positive is just telling me the sign on the energy is it being gained or absorbed or emitted. I'm emitting that energy, and that's why it's negative. I don't want to actually give myself a negative distance, though. So I find here the wavelength to be 1.21 times 10 to the minus 7 meters. And n equals 2 going to n equals 4. This means n equals 2 is n initial, n equals 4 is n final. That, in this case, the energy is actually being, or the photon is being absorbed, exciting that electron to a higher energy level. Negative 2.18 times 10 to the negative 18th joules. 1 over 4 squared minus 1 over 2 squared gives me 4.09 times 10 to the negative 19th joules. Again, positive in this case because the electron gained that energy to emit up to a more excited energy state. Plug all of this in. Lambda 6.626 times 10 to the minus 34 joule seconds. Speed of light, 2.998 times 10 to the 8th meters per second. And the energy we just calculated, 4.09 times 10 to the negative 19th joules. And I get 4.86 times 10 to the negative 7 meters. Make sure you're comfortable doing these calculations for the transitions of the electrons between the different energy levels. Which electron is, on average, closer to the nucleus? An electron in a 2s orbital or electron in a 3s orbital? Well, remember, what do these 2s and 3s mean? The 2 and the 3 tells you your energy shell. So you've got your nucleus with your protons and your neutrons hanging out. And then you've got your shells. N equals 1, N equals 2, N equals 3, and so forth. In the N equals 1 level, we have 1s orbitals. In the N equals 2 orbital, we have 2s and 2p orbitals. In the N equals 3, we have 3s and 3p and 3d orbitals. N equals 4, 4s, 4p, 4d, and 4f. And then from then on, we've got 5s, 5p, 5d, 5f, etc. of each type of orbital. But that means that the nucleus is here. So closest to the nucleus is our 1s. But if I'm comparing 2s and 3s, I see 2s is in fact closer to our nucleus than a 3s orbital would be. So you need to think about what those orbitals mean in relation to the structure of the atom itself and where they reside. What are possible values of L for each value of N? What is L? L tells me the type of orbital I have. meaning is it S, P, D, or F? L equals 0 gives me an S orbital. L equals 1 is P. L equals 2 is D. And L equals 3 is F. L is equal to n minus 1 and anything below that. So if what I mean by that is n equals 4, I can have L equals 3, L equals 2, L equals 1, down to L equals 0. It's always L equals 0 up to the value of n minus 1. So if n equals 1, that means L can only equal 0. If n equals 2, L can equal 0 or L can equal 1. If L equals 3, if n equals 3, should be an n there, L could be equal to 2, L could be equal to 1, or L could be equal to 0. And if n equals 4, L could be equal to 3, to 2, to 1, or to 0. This would be an s orbital. These are p orbitals, d orbitals, and f orbitals. Again, quantum numbers are just the address of the electron. They're just a mathematical way for us to describe where these things reside. What are the possible values of m sub L for each value of L? What is m sub L? M sub L is equal to negative L through 0 through positive L. So if L equals 0, m sub L has to equal 0. M sub L also describes the orientation of the orbital. Because remember, s orbitals, we only have a sphere. That should be a sphere. P orbitals, we have px, py, and pz. So we've got dumbbells. D, we have 5 options, and F, we have 7 options. M sub L is telling me which of those options I have. So if L equals 0, we can only have m sub L equal to 0. This is going to represent an s orbital. If L equals 1, m sub L can equal negative 1, 0, or positive 1. These are the 3 p orbitals. If L equals 2, m sub L will equal negative 2, negative 1, 0, plus 1, and plus 2. Your 5 d orbitals. And if L equals 3, m sub L is equal to negative 3, negative 2, negative 1, 0, plus 1, plus 2, and plus 3, which is your 7 f orbitals. Sketch the 1s and 2p orbitals. How do they differ and how many electrons does each orbital hold? 1s is a sphere. 2p is your dumbbells. So this is your 1s. This is 2p, 2p, and 2p. Each shape holds 2 electrons. So this holds 2 electrons. This in total holds 2 electrons. This holds 2 electrons, and this holds 2 electrons. So the s orbital holds 2 electrons total, while your 3p orbitals hold 6 electrons total. S is a sphere. Oops. P is, I call them your dumbbells. Other people call them bow ties. Whatever you want to call them. But that's the difference in shape. And then these will actually have opposite, talk about this in another class, but one side will be shaded in, one side will not. So they're slightly opposite of each other, but this makes up your 2p, 2px, 2py, 2pz. The emission spectrum of sodium consists of 2 closely spaced yellow lines that are both around 589 nanometers. What do I mean by that? What do I mean by the emission spectrum? Well, that comes back to when I look at, if I looked at sodium lamp through a spectrum specifically. So this whole thing is going to look like black light behind the scenes, okay? So we've got this black light. Let's pretend this is a solid black light. And if we looked at this through a gradient, through a diffraction gradient, or through a prism, what we would find is 2 yellow lines closely spaced around 589 nanometers. I want to know what's the frequency of light that's showing at 589 nanometers. So if I have these lines coming through my emission spectrum and I read them at about 589 nanometers, I want to know what is the frequency of light associated with that wavelength. Well, I know lambda is equal to c over nu, and that is the relationship I can use to relate wavelength and frequency. Because again, lambda, wavelength, c is speed of light, which is a constant, .998 times 10 to the 8th meters per second. And nu, it looks like a V, but it's pronounced nu, like NU, it's a Greek letter, is your frequency, which has units seconds to the -1. So I want to know the frequency of 589 nanometers of light. Now you can do this in 2 steps. We do have to convert this nanometers to meters because we're going to be combining it with speed of light. I'm going to do that in one equation. You can split that up into 2 pieces if you'd like. I'll show you what I mean in a sec. First, we need to rearrange this equation. I'm going to algebraically rearrange this to solve for the frequency. So to solve for frequency, it will be the speed of light divided by your wavelength. I'm going to plug in my variables, what I know, 2.998 times 10 to the 8th meters per second, and I have 589 nanometers. Now I cannot do the calculations straight out like this because my units will not cancel. I'm trying to solve for frequency, which has units of seconds to the -1. Put that equal sign in the wrong spot. Seconds to the -1. This right here is my seconds to the -1. So I have that. That's perfect. I've got that. But I've got to cancel out my meters. The way to do that is to convert your nanometers to meters. Now I'm going to do this in the same equation, but you can do this separately. You could separately in your calculator say 589 nanometers times 1 meter divided by 10 to the 9th nanometers and calculate it out, or you can do it in the same equation. You have a few different conversion factors you can use. You can use, like I have written, 1 meter or 10 to the 9th nanometers. Or you can write this as 10 to the -9th meters to 1 nanometer. We must have meters on top and nanometers on bottom, though, because we're trying to cancel out nanometers and get to meters. These are the 2 options you have. How do I choose which one I want? I like bigger numbers. I don't like this. My brain doesn't like it. It doesn't matter to me. Some students are really still confused on how to keep them together. Basically, a nanometer is a really, really, really small number, so I know it has to have a whole bunch of them to equal up to 1 meter. What this means is that 1/1 billionth of a meter equals 1 nanometer. So it's got to be a really small number, and I know that a negative number makes it small. I don't know if that helps. That's just how my brain sees it. So I'm going to plug this right into the equation here, though, instead of doing it separately. And when I do that, that cancels out my nanometers. That cancels out my meters, and I'm left with my seconds to the -1, which is my frequency, also known as hertz. Calculate this out, and I get 5.09 times 10 to the 14th seconds to the -1. So again, if you wanted to calculate this separately and get some value here and plug it in, that's totally fine. I don't care. You're welcome to do that. I just like doing them in one fell swoop because it just makes it easier. And that way I plug them in my calculator all together and I'm less likely to make an error. What is the energy of 1 photon of light with a wavelength of 589 nanometers? Well, the equation we have for that, energy is equal to hc over lambda. This is what relates energy and wavelength. So I'm asked for energy, and I've got a wavelength given. I've got to think about what correlates those two pieces. This is the equation I have. I have Planck's constant. Planck's constant is 6.626. There is 4 sig figs there. Times 10 to the -34 joule seconds. Times 2.998 times 10 to the 8th meters per second for the speed of light. And divided by our wavelength. Now, just like before, we're going to have to convert that wavelength into meters. So I'm going to say 589 nanometers times 1 meter divided by 10 to the 9th nanometers. Again, you can do that separately if you'd like, or if you calculated it before for part A, you already have it calculated for part B. That's fine too. Let's check our units here. We've got nanometers canceling, meters canceling, and seconds canceling, and we're left with joules, which is exactly what we need. This gives me 3.37 times 10 to the -19th joules. And what is the energy of 589 nanometers of light in kilojoules per mole? This is for 1 photon. It's a really small number. -19, that's a really small number. I want to know how much this is in units of kilojoules per mole. So I'm going to take, I know how much it is for 1. I'm trying to find in kilojoules per mole. I know for 1, it's 3.37 times 10 to the -19 joules for 1 photon. Now, how am I going to do this? Well, I need to remember Avogadro's number. I know you guys know it, but a lot of people don't think about it in this relationship. I know that I have 6.022 times 10 to the 23rd photons per 1 mole of photons. That's how I'm going to convert it to per mole. I'm going to figure out how many photons I have in an entire mole. This is for 1 photon. This is for a mole of photons. And then I'm going to convert that to kilojoules. It's 1 kilojoule per 1,000 joules. And I get out 203 kilojoules per mole. So I found that the frequency of 589 nanometers of light, sorry, that color is hard to see, is 509 times 10 to the 14th hertz, or seconds to the -1. The energy of 1 photon of light with a wavelength of 589 nanometers is 3.37 times 10 to the -19 joules, and the energy of 589 nanometers of light in kilojoules per mole is 203 kilojoules per mole. Consider the following portions of the electromagnetic spectrum microwave radiation, X-rays, green light, and orange light. Can you place these things in order of increasing wavelength, increasing frequency, and increasing energy? Increasing means lowest to highest. And wavelength is a distance, so it's like shortest to longest. So we've got X-rays, green light, orange light, and microwaves. These two are both in the visible region. X-rays are really high energy, which means they have really short wavelengths. Remember, the longer the wavelength, the lower the energy. Wavelength and energy inversely proportional. Microwaves have really long wavelengths, really low energy. So increasing wavelength, X-rays would have the shortest wavelengths because they're the highest energy. Microwaves have the longest wavelength. They're the lowest in energy. Then it comes down to orange and green light. This one is kind of hard to think about. You've got to think about the electromagnetic spectrum and then try to remember the pattern of the rainbow, which sounds easier than most people make it. It's actually not as simplistic as you think about because we kind of actually memorize this backwards. So what I mean by that is if you think about the electromagnetic spectrum, we've got radio waves, microwaves, got X-rays, gamma rays. Somewhere in the middle here, we've got the visible region. This is an increase in energy over here and a decrease in wavelength. This is a decrease in energy, increase in wavelength. But what about in the visible spectrum? We've learned this mnemonic, Roy G. Biv. Red, orange, green, blue, indigo, violet. Or red, orange, yellow. I forgot the yellow part of that. I'm sorry. The Roy part. Red, orange, yellow, green, blue, indigo, violet. At least in the US, this is the way we've memorized. I've had some students from Asia that have actually memorized the backwards direction, what I consider backwards, but actually more helpful here. The problem with this is that this is actually memorized backwards to the electromagnetic spectrum. What I mean by that is the spectrum itself actually has violet with the highest, indigo, blue, green, yellow, orange, and red. So be careful if you're using this mnemonic to remember the order of these things. What this means is if I'm looking at orange light and green light, orange light and green light, orange light actually has a longer wavelength and lower energy. Green light, on the other hand, has a shorter wavelength and higher energy. So this will be green light, orange light, and microwaves. What about increasing frequency? Lambda is equal to C over nu. They're inversely proportional. Energy is proportional to frequency, but lambda is proportional to the inverse of your frequency, meaning that as energy increases, your frequency also increases. As energy decreases, your frequency also decreases. So if I want to increase the frequency, this will go the opposite direction. I want the lowest frequency to the highest frequency. Lowest frequency is going to be my microwaves. Next will be my orange light. Followed by green light. And the highest frequency in this list will be my X-rays. What about decreasing energy? I want to go from highest energy to lowest energy. Decreasing means highest to lowest. I know that probably seems intuitive, but when you guys are stressed out or under the time crunch of a quiz or exam, that's when students mess that kind of concept up, and they don't think about, they get really stressed out on, well, what do you mean by increasing? What do you mean by decreasing? I mean, it goes from highest to lowest or lowest to highest. So I want the highest energy first. The highest energy will be your X-rays. Next highest energy would be green light, followed by orange light, followed by microwaves. Okay. If an electron in a hydrogen atom makes a transition from the n equals 3 to n equals 5 state, can you answer the following questions? Was the energy emitted or absorbed? Well, let's think about what this means. We've got your nucleus here. N equals 1, n equals 2, n equals 3. We'll pretend these are circles. N equals 4, and n equals 5. So I've got an electron here, and it transitions from the n equals 3 to the n equals 5 state. So it ends up here. Does that mean energy was emitted or energy was absorbed? That means energy was absorbed. That electron absorbed energy in order to make that jump to a higher energy level. Because of that, I expect the energy change here to be positive because it gained that energy. What is the change in energy? For this one, you're going to use what I call the Rydberg equation with the Rydberg constant. Negative RH times 1 over n final squared minus 1 over n initial squared. Rydberg constant is 2.18 times 10 negative 18 joules, so a negative Rydberg constant, negative 2.18 times 10 to the negative 18 joules, times 1 over n final. N final is the final energy state you were in. So we ended at 5, so it's going to be minus 1 over 5 squared. And initial is our initial state, which was 3, so 1 over 3 squared. Calculate this out. And this does have 3 sig figs in it. These are exact numbers. So I'm going to limit this to 3 sig figs, 1.55 times 10 to the negative 19th joules. And lastly, what wavelength of light was emitted or absorbed? Well, we know it was absorbed. Just in case, we already figured that out. The wavelength was absorbed. But what wavelength of light was it? In order to correlate wavelength with, right now I have energy, and I want to know the wavelength, I'm going to use E equals hc over lambda, and I'm going to rearrange this equation to solve for lambda. Remember, lambda is wavelength. Lambda equals hc over E. H and C are both constants. E is the energy we calculated in part B. So this is equal to 6.626 times 10 to the minus 34 joule seconds, Planck's constant, times the speed of light, 2.998, times 10 to the 8th meters per second, which is the speed of light, divided by our energy, 1.55, times 10 to the negative 19th joules. Just to check, make sure units are canceling. Joules and joules, seconds and seconds. This solves out to give me meters, 1.28 times 10 to the minus 6 meters. Now, we very, very rarely report wavelength in meters. We usually report it in nanometers. So I'm going to convert this to nanometers. So times 10 to the 9th nanometers to 1 meter. And I find that my value is 1,280 nanometers. Writing it like this, 1280, gives me 3 sig figs. 1, 2, and 3. This 0 is ambiguous. It's insignificant. It's a placeholder. It's not significant because I didn't put a decimal place at the end. So this does have 3 sig figs. Okay. What is the wavelength range of visible light? This is just something you should just generally know. It's roughly 400 to 750 nanometers. This is where we see everything. The entire electromagnetic spectrum, and we see here. I think that's kind of cool. We think we see so much, but yet we really see a very small snippet of the world. But this is where visible light is shown, and this is where we observe everything. Okay, the Paschen series of the atomic emission spectrum occurs in the infrared portion of the electromagnetic spectrum. Lines in this series result when an electron makes a transition from a higher energy state to the n=3 energy state. One of the lines in this series has a wavelength of 1093.8 nanometers. Which energy state was the electron originally in? So, higher energy to n=3. And I've got a wavelength of 1093.8 nanometers. And I want to know where this thing came from. Well, let's see. I know that I have a wavelength here, so I'm going to figure out what the energy was of this, that resulted from this wavelength emission. Energy is equal to hc over lambda. H again, Planck's constant, 6.626. Times 10 to the minus 34 joule seconds. Speed of light, 2.998 times 10 to the 8th meters per second. And wavelength, 1093.8 nanometers. I do need that in meters, so I'm going to convert that to meters. That cancels out my nanometers. That cancels out my meters. That cancels out my seconds. This is going to give me the energy transition. 1.82. Oh, sorry, I should keep one more sig fig there. Let me actually check this on the calculator really quick because I didn't write down the right number of sig figs. 6.626 times 10 to minus 34 times 2.998 times 10 to the 8th divided by 1093.8 converted to, okay, 1093.8 converted to meters from nanometers. 1.816. I have 4 sig figs here, 4 here, and 4 here, so I do need 4 sig figs. Times 10 to the negative 19th joules. Now, this is the energy associated with that wavelength. So it's a transition resulting in the wavelength of 1093.8 nanometers. I'm going to use the Rydberg constant. So Rydberg constant, your energy is equal to negative RH times n final squared minus 1 over n initial squared. N final being your final level, your final energy level, and initial being where it started. Here's the thing. This tells me it goes from a higher energy state to the n=3 state. This means that I've got your nucleus here. 1, 2, 3, 4, 5, whatever it's coming from, okay? So n=1, n=2, n=3, n=4, n=5. That means I've got, say it's n=5. I don't know, but we'll figure out the answers in a sec. I've got something going from here down to this level, which means it's losing photon of light at the wavelength 1093.8 nanometers. So energy, we did calculate it has this change in energy. It's a positive wavelength because wavelength is distance. Wavelength has to be a positive value. But because I'm losing that energy, I need to realize that I need to put a negative sign in front of this value when I plug it in my Rydberg constant. And that's because I'm losing the energy. In chapter 7, we talk about the perspective of the system. In this case, the system is, where your energy is traveling from. It's going higher energy to lower energy level. Therefore, it's losing that energy. So when I put the numbers in here, I'm going to write negative 1.816 times 10 to the negative 19 joules equals negative 2.18 times 10 to the minus 18th joules. Now my final energy state is n equals 3 because that's the definition of the Paschen series. So 3 squared minus 1 over n initial squared. I'm trying to solve for what this value is. That's what I'm trying to find. I'm going to go ahead and simplify this up a little bit. Negative 1.816 times 10 to the negative 19th joules divided by negative 2.18 times 10 to the negative 18th joules equals 1/9 minus 1 over n initial squared. This is the same as 0.08349. I'm going to underline the 4 here because that's where my sig figs are. In the end, they're not going to matter much because I'm going to have to be solving for a single number. But I do have 3 sig figs here, so this is reduced down to 3 sig figs. And this equals, again, 1 over 9 minus 1 over n initial squared. I'm going to continue the calculation up here. Let's change color just so we can try to keep our eyes clear on where we're going. And I'm going to isolate the 1 over n initial squared by I'm going to bring it to the other side. So basically, let me slow this down and I'll erase this in a second. Let me do this in multiple steps. What I'm doing here, I'm taking this equation and I'm adding 1 over n initial squared to both sides. So I've got 0.08349 plus 1 over n initial squared equals 1 over 9 minus 1 over n initial squared plus 1 over n initial squared. The reason I do that is that cancels these out and it gives this a positive value. I like positive numbers. I then am going to subtract 0.08349 from both sides of the equation. And what I get as a result here, when I do all this, basically all this algebra, I get 1 over n initial squared is equal to 1/9 minus 0.08349. I usually do that in one fell swoop, but sometimes it confuses students when you move things and they become negative all of a sudden, or positive all of a sudden when you move them to the other side. So now I've got 1 over n initial squared equals 1 over 9 minus 0.08349. I'm going to simplify that. 1 over n initial squared equals 0.02762. The 1 over 9 is an exact number, so it's not going to limit my sig figs per se. Now what I'm going to do is I'm going to algebraically manipulate this. So I'm going to multiply both sides by n initial squared. And I'm going to divide both sides by 0.02762. If you're unsure what I mean by that, come see me in office hours because it's kind of hard. I'm running out of room on the slide, to be honest with you. But it's an algebraic manipulation that results in n initial squared equals 1 over 0.02762. This equals 36.2. So n initial squared is equal to 36.2. I can then take the square root of both sides, and I find that n initial is equal to 6. So what does that mean? All this work we just did, what does that actually mean? Pause the video if you need to write this stuff down because I need to erase some stuff to explain what I mean. Basically what we just solved, we've got your nucleus in the center, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and n equals 6. I'm just going to put little numbers here so that make it easier. 1, 2, 3, 4, 5, 6. What I just figured out is I have an electron that if it travels from here to the n equals 3 level, it will release a photon of light at a wavelength of 1093.8 nanometers, specifically for hydrogen. Now, some people may ask, why do we care? It's a great question. We care for a lot of reasons. We care because, like, this is how we can figure out what stars are composed of. We can figure out how old they are. We can figure out all kinds of things just by the wavelength of light emitted from a substance or a species. So there's lots of reasons we actually do care. Okay, 17. I love this question. This really pulls in concepts from chapter 7, or thermochemistry and the electromagnetic spectrum. So, a microwave oven heats by radiating food with microwave radiation, which is absorbed by the food and converted to heat. Suppose an oven's radiation wavelength is 12.5 centimeters. A container with 0.25 liters of water was placed in the oven, and the temperature of the water rose from 20 degrees C to 100 degrees C. How many photons of this microwave radiation were required? Assume all of the energy from radiation was used to raise the temperature of water, so we're assuming no loss to outside factors. Let's see, we're told the wavelength here is 12.5 centimeters. It's a pretty long wavelength. I'm going to convert that to meters, which is 0.125 meters. I know energy is equal to hc over lambda. So I can use this to find the energy coming off of that one wavelength. Planck's constant, 6.626 times 10 to the minus 34 joule seconds. Speed of light, 2.998 times 10 to the 8th meters per second. And wavelength, 0.125 meters. This gives me an energy of 1.589. I'm going to underline that because I don't want to round yet. I don't want to create round off error. But my sig figs are at 3. 1.589 times 10 to the minus 24 joules. But this is for one photon. The wavelength that's coming at, all the photons come out at the same wavelength. But if I calculate this, this equation is giving me the energy for one single photon. I want to know how many photons do I need to heat up all of this food, heat up this sample of water I have, 0.25 liters of water, from 20 degrees to 100 degrees C. In order to do that, I first need to figure out how much energy is required to actually increase the temperature of water that much. To do that, we're going to use our MCAT equation. Q equals mc delta T. So again, we cover this in the thermo chapter. Well, what is our mass? We've got 0.250 liters of water. Water has an approximate density of 1 gram per mil. It does technically depend on temperature, but we're going to assume 1 gram per milliliter for the density of water. We've got 1,000 milliliters in 1 liter. So my liters have canceled, my mils have canceled, and I've got grams, which is what I need. So I assume this to be 250 grams of water. I'm going to put a decimal place at the end of this 250 because this has 3 sig figs, so this must have 3 sig figs as well. C is our specific heat, 4.184 joules per gram degree C for water. And delta T is your temperature final minus your temperature initial. So plug in everything we know. We've got 250 grams of water times our specific heat, 4.184 joules per gram degree C, times our final temperature, 100 degrees C, minus our initial temperature, 20 degrees C. Calculate all this out, and you're going to get a Q, or a heat value, of 83680. We have 3 sig figs here, so I'm going to go ahead and underline that 6. So it will take 83,680 joules to heat 250 grams of water from 20 degrees C to 100 degrees C. How many photons of this microwave radiation required to be able to bring up this much heat? I've got 83680 joules that are needed, and each photon emits 1.589 times 10 to the minus 24th joules. That gives me an answer of 5.27 times 10 to the 28th photons. How many moles of photons is that? Take 5.27 times 10 to the 28th and divide it by Avogadro's number. It's a lot of photons. Photons are really, really small. Plus, it does take a little bit of energy to raise water from 20 degrees C to boiling. Hope this helps.